What we're going to be going over here is we're going to be calculating the eigenvectors and eigenvalues here of a quadratic function, and we'll be specifically looking here at our quadratic as an ellipsoid here in really 3 dimensions. Okay, so what we want to do here, really what we're going to be doing is just going over and setting up our algebraic matrix here to determine what our eigenvectors and eigenvalues are for this particular quadratic function we have here. So you're going to see when we talk about a quadratic function here, we have some squared terms, and we really got 3 different dimensions here. X, Y, and Z are 3 different coordinates. And it would be the squared terms here for X, squared terms for Y, squared term for Z times some coefficients for each of those. And then you're going to have these cross terms in here. A YZ is XZ and an XY, and it can be any number of those different cross terms here. And then you can have one single value here. Okay, so when you're dealing with these eigenvectors and eigenvalues, what you essentially do here, you take that quadratic function and you're going to eliminate those cross terms. And really, if they are minor in value and they really don't affect the problem that, or the figure that you're looking at here, the diagram that you're looking at in this case, or has little influence on it, you get rid of them. And then what you do is you just transfer it over into the case here where we look at these eigenvectors here into unit amounts here, just a unit amount. So what we're going to do here is we're just going to make the calculations of our eigenvectors and eigenvalues. We're not going to show how we make the transformation, but you should understand when you're dealing with these eigenvectors and eigenvalues here, it involves a translation here. Okay, so what we would do here, and we'll look at it here in terms of our ellipsoid here, and you can see this ellipsoid here. This is really what we're starting with, and when you're working with these problems, you really should have some idea of the diagram or the figure that you're looking at here. So this ellipsoid here, I've cut a hole in it here, and I'm just showing the axis that it's sitting on here, the X, Y, and Z, blue, red, and green here, and then this point here is really the 0, 0, 0 point here for our ellipsoid here. But you can see it's skewed off here based on our original, our solution, our quadratic function that we're dealing with these x, y, and z terms, or cross terms here between x, y, and z here. Okay, so what we essentially doing is when we calculate these eigenvectors and the eigenvalues, really what you're doing is you're straightening out this, getting rid of those cross terms or those minor elements here that affect your function that you're looking at. And what you do is you transfer them into really looking at squaring up your problem here and making it more, in this case it becomes well, they're perpendicular over here, but there's these axes x, y, and z, but they're skewed off at different angles here. And what you do is you just come up with these eigenvalues here and vectors, and you try to come up with some solution point here where you're going to have really take rid of all those the erratic part of that function here and put it into just a nice even curved function here that you can deal with. Okay, so we're not going to be dealing with how we get to these axes here, x, y, and z, when we by eliminating our cross terms. We're just going to work with coming up with our eigenvalues and our eigenvectors. So you get an understanding of what you're looking at here. And then if you go down here and look at it, these are eigenvectors I'm showing it here. This arrow here, red, and then we got blue here, and we got some tangent plane here, and then I've got this green one here. Now, these eigenvectors, what you're doing with them, you have to come up with a solution point here where they're all less, there's some fractional amount here, a decimal amount less than 1 here. Or they can be equal to 1 here. And when I say equal to 1, that's x, y, and z here. Those eigenvectors here, they really control the direction here of this function that we're looking at here. But what we would do here, and when I say equal to 1, that's when we're talking about making this rotation here. Just to make that point clear here. And by making the rotation, you can see we're sitting at, in this case, with our eigenvector here, with the problem I'm looking at, I got a 90-degree angle here between our green vector here and our red and blue. And the red and blue make up our tangent eigenvector plane here. And the green one here is really an important vector here that's perpendicular to the other two. And what we would do here, we would, when we come up with our solution, and we're not going to do it here, these actually rotate over by 90 degrees here when we come up with equal to a unit of 1 for each of these eigenvectors here. If in this place here they're less than a unit of 1, and we'll calculate those, it'd be like 0.96, 0.60, and so forth here. Okay, so you get an idea of what's going on. We're only going to deal with coming up with the eigenvectors themselves here. And then if we go down here, this is what we talk about the eigenvalues. They're really just a scalar amount here of the eigenvectors. Whatever, if the eigenvector here is like 0.7, the eigenvalue would be some scalar amount of that. So if you had 0.7 here and your eigenvalue was, or you would scale it up by 10, then this vector here, whatever one it would equal 7. You know, get the idea what's going on here. But these eigenvalues here are just a scalar amount of the eigenvectors. They really control the magnitude that we're talking about with these vectors. With the with the vectors here, eigenvectors, they control the direction, the x, y, z direction in this case, whereas the eigenvalues control the magnitude or the amount that we're making that, what it's equal to here with our function. Okay, so that's just a rough idea of what we're looking at. So let's go up and let's really look at it over here. So what we're going to be doing here, we're dealing with an algebraic solution here. That's what we're trying to come up with. So this is the general, this is the most important part here, because you're going to use this formula. You're going to set up a square matrix, a symmetric square matrix, and based on that matrix, then you can come up with an algebraic computer solution for determining your eigenvalues and your eigenvectors here. So here we're going to just look at the general way we would set up the symmetric square matrix here. So this is our function that we're looking at here. This is our general quadratic function. And in this case, I've got an ellipsoid here. But you'd have here, this is the function, and I got it broken into two. It's really just one continuation here. You're going to have some coefficient times some squared terms, a coefficient, that was coefficient A, coefficient B times some y squared term here, plus coefficient C times some z squared terms here. So these A, B's, and C's, they just represent some values here. And then, so those are our squared terms, and then for our cross terms, you're going to have, in this case, we're going to be looking, you look at x, z cross terms, x, y cross terms, and then y, z cross terms here. And then you have some coefficient amount times each of those. And then you have your lone or your individual terms here for your x, p times, coefficient p times x, coefficient q times y, plus a coefficient r times z. And then you're going to have just one individual term here, just one unit term here, and that's all set equal to 0 here. So that's what we're dealing with, and what we have to do here to come up with this algebraic solution, and it's very good a way of resolving this problem here, is we have to set up the symmetric matrix. So this is the way it's done here, and this is the general solution that you want to look at. You're going to have, in this case, we're going to have a 4x4 matrix. I got the 3 axis, x, y, z, and then we have a unit of 1 here. That's a unit of 1. So we got really a 4x4 here. So we got the axis is here, and then we got that unit point here, 1. And those are across our horizontal axis, across our top. These really represent the columns that we'd be looking at for x, y, and z. And then along the side here, I've got the rows here. X row, y row here, and z row. And then we got that unit of 1 here. Okay, so let's take our symmetric, our general quadratic formula here. Now, when I say a general formula here, when you're dealing with these problems here, you may not have certain cross terms, and you may not have x, y, and z. You may just have x and y squared here, just working in a 2 dimensions and so forth. So this is just the general solution. So this is what you're going to have to do here. Set up your matrix in this fashion. I told you x, y, z, and 1. Those represent our columns. And then our rows are x, y, z, and 1 here. And really what you're doing here, with these quadratic functions where we're trying to get everything squared up here, you're really dealing with a diagonal here, and then an upper triangular matrix here. It's really 3 by 3. but it's triangular. And then what we do here with this triangular matrix, we add it, well, we divide it up here. We take it, when we'll look at those terms here, we're going to set this triangular one up here, and then we flip it over here essentially and set up a lower triangular matrix here. Okay, so let's go and let's look at our problem here. So our general, this is general solution. So first off, look at our diagonals here. Okay, ax squared, bxy squared, and cz squared here. So we'll put that on our diagonals here. So for our x column and our x row here, that's where you have a, coefficient a, whatever that is, times xx. I put it out ax squared here, just so you can clearly see it here. And then when you come down to your y row, y column, you're going to have that b, y times y times y, or y squared. See them up here? Ax, a times x squared, b times y squared, and then you would have the last one would be c times z squared here. C times z. So that's your row here and column here. Okay, so you got your diagonal here, and then you got that last term here. What if you got some amount here? You'd put that in. It's a single value here, some number amount. So you put that d in here, and that key here, that's the key here. It lines up with 1 here. It's a coefficient of, or not a coefficient, but it's times 1. A column of 1, a row of 1 here, that last one. Okay, so we've taken care of our diagonal. Now dealing with our cross terms here. This is what the key to the whole thing. This is what makes this problem symmetric here. Okay, so what we would do here, let's look at h, y, and x here. So we have an x row, y column, just to get, so do we have one of those here? Well, we would, because I got everything shown. So we take half of this h here. So everything is divided in half. This h, x, y here, y, x here, take half of that. Half of it, just divide it by 2. And then the mirror part here, the flip part of it goes into x, or you got x, y here. So you got hyx here, where you got the hxy term here. Anyway, you're just multiplying. Just understand you have to make that symmetric flip here. So again, half of that. So we've just taken this h here and we divided it into 2 halves here. Upper triangular half here, and that lines up with the xy term here, and then the lower triangular hyx. It doesn't matter here, x, y, yx. It's only to understand that how you have to divide them up here. So you're going to do the same thing for your your xz term here. Let's look at that. gxz, that's sitting here. So 1/2 of that. So what would that be? The z here column, x row. Okay, so where does that go in? That's on our upper triangle. Where would the amount go for our lower triangle? Over here. So here it's zx. I had xz here. Just understand that they're multiplied time. Again, 1/2 here. And you do the same here for your f term here, your coefficient f times yz here, yz. That goes here, y row, z column. And then where would that go? That's in our upper triangle. So our lower triangle, it goes to right over here. Y column, z row here, f, z, y here. Okay, just so you see they're dividing them up. And then for these unit amounts here, just looking x, y, and z terms here individually, you get the p, q, and r here. All I'm doing is, this is where I set in that column here of 1 here, both row 1, column of 1. So 1/2 of px here. So the other half goes over here, px. So that would be x column, row 1. And then for qy, just to get an idea here, you got your qy, so that would be column 1 here, and then that would be row, let's see here, qy, where do we sit here with qy? Okay, here it is, row 1, column y. Okay, get the idea. And then for rz here, remember those are the coefficients here, r is the coefficients, so z, and then remember that's 1/2. Everything's getting divided up in half to make this matrix symmetric. Okay, so what are we sitting with here? R times z here, and that it goes into row z, column 1, and then column 1, or row 1, column z. So that's how it works. So the key is here, once you get your function here, lay that function out, and then you have to divide everything up here. You have to set up your diagonal with your squared amounts here, x, y, and z, since we got 3 terms there, and then just divide up all your cross terms here. And they have to be set up, I'm just showing, and they have to be divided here equally. Take half goes on the upper triangle wherever it lines with your column row here, and the other half goes into the lower triangle wherever it lines up with your column row here. Okay, so that's a general solution, and really what that's going to give us here, we're going to have those, the eigenvectors are really going to be the solution to this general matrix here. But our eigenvalues here, well, they actually straighten, I'm looking at this little function, our ellipsoid here. They're going to actually straighten it out here, but that's not what we're going to be getting into here. We're just going to calculate them. Okay, so going to our function here that we're dealing with. So let's set that up here. Okay, so we got our x, y, z in one columns here, and then rows across here, x, y, z here. So for our x term, 103 times x squared, that would go here, x times x here, 103. And then for our y squared, 125, that's y column, y row. And then what do we have here? 66 for z squared. Okay, so you can see these aren't being divided up. They're just sitting on this diagonal. It has to be a symmetric matrix, a square matrix. In this case, it's a 4 by 4 matrix. And then that last term here, minus 294, we just put it in here. Column 1, row 1 here, minus 294. And then what do we have here? We got a cross term here, y, z minus 60. So where does that go in here? So z, y here, minus 30, half of the minus 60. And then the other half goes in here, minus 30. That's z, y, or yz, however you want to look at it. Didn't change signs. All we did is divide it in half. And then we got that 12. We got a 12xz here. Where does that go? So we got our z, x here, x row, z column, minus x. And then that's half of it. And then the other half goes down here. It goes into z, x, again, minus 6 here. And what do we have here? That's taken care of. And then we got that 48 here, 48xy. So what do we have here? A minus 48. It was minus 12 here, minus 60 here. Minus 48, so we got half of that's 24 here in your y, x. And then the other half goes in here, 24x. Y. Okay, and then we got that last number here, minus 294. That just goes into your column 1, row 1 here. Okay, so what we're doing here, we set up our diagonal, we got our matrix, and we're going to work off this matrix here. The algebraic solution to come up with our eigenvectors and our eigenvalues. So here's this is the symmetry that we're really coming up with here. We'd have to make some, you have to do some translation here, but this is the symmetry for that ellipsoid here. We had the skewed one, and this is where everything squares up here. So what we're doing here, with this matrix and with our algebraic solution, we're coming up with an axis of symmetry, and it's a line or lines that divides the figure into 3 symmetrical parts. We got our x, y, and z axis here with these little blue dots here, green for let's see, z axis, blue for our x-axis, and let's say our y-axis is red here, vice versa, whatever. But it divides the figure into 3 symmetrical parts in such a way that the figure on one side is a mirror shape of the other side. So that's what we're going to do. If I rotated this ellipsoid around here, you would see what we're talking about. I actually cut a hole out in this ellipsoid so you could see where our 0, 0 point is here. And by setting up our matrix here, symmetric, you can see it's very symmetric. The diagonals, well, that's on a diagonal here, whatever we're going to come up with here. And really those diagonals are going to turn them into eigenvalues here. But you can see how symmetric it is here. Each side, minus 24, minus 24, minus 6 here, minus 6 here. And remember, that lines up with zx here, or xz, and so forth here. Minus 30, minus 30. And then this single number here lines on our diagonal here. Now you notice I didn't have any x, y, and z terms in here for this problem. I'm only looking at your cross function here. I don't have any individual functions. Okay, so now we'll just go in and we'll use this matrix, this square, the symmetric matrix, just to calculate our eigenvalues and our eigenvectors. Okay, now let's look at our computer solution, or the software solution that I'm going to use to determine our eigenvectors and eigenvalues based on our quadratic function here, this ellipsoid that we're looking at. Okay, so we've set up our matrix here with our columns across the top, rows on the side here. We have their matrix. That's what we just calculated. So what we're going to do here, the first thing, let's just understand what's going on here. I've got this command here, and I'm using MapleSoft. I just say I do a transpose here, a vector x, y, z here, our columns across the top, times our A matrix here, times our vector here, x, y, z, our rows across the side here. And what we do here, I got another command that says just evaluate this here, the x, y, z in one terms times that A matrix at, again, times the x, y, z one rows here. And that's going to give you some polynomial here in x, y, and z terms. And what that is here, just understand the basics of what's going on here. That first row here, 103 minus 24 minus 6, let's look at that. The 103 was for the x, minus 24 here was for your y column, and minus 6 was for your z column. And that's all taken times the first row here, row x. And the same for the next ones here. Then you just have minus 24 here for the x term, 125 here for the y term. Remember, that's on our diagonal here. And then minus 30 here for your z terms. And that's all times y. So you see what's going on here. X you take times each one of those. So the x times your 103, x is x squared, and then the other cross terms here. And y, well, you take y here times your 125. That gives your squared terms, and then the other ones are the cross terms. And then finally, just that last row here. That's using that evaluation. Minus 6, minus 30, so minus 6x minus 30y plus 66z, that's our squared term, all times column Z here. And then we have that minus 294 here. Then you just simplify that here. This is a Maple command here, evaluate. We simplify whatever our evaluation was here. And what it does here, it's just coming back to our general quadratic equation, or specific quadratic equation we're working with that ellipsoid. So you could go back and look at that. But I'm just saying this is what you're doing here, and you can see by using this technique here, I still can't determine x, y, and z because of this polynomial. If you got some way of solving it with some software, that's fine. I don't here. So I come up with this polynomial. Just to understand how I got my rows and columns calculated here for each of those here. All right, but what you do have here, whatever software package you have, you can just call, we could have just looked at it in these terms, just call out your eigenvalues here based on whatever matrix you're working with, and here they are here. Eigenvalues minus 294, 147, 98, and 49. And I also can have a call out here for eigenvectors here, and it's going to give me a column form here for each of those here, x, y, and z axis, and then also that unity axis here, one. And they just match up with my eigenvalues here. I just wanted to go through this so you understand what's going on and why we use this lambda term here to come up with our solution. So let's go and look at that. Okay, so we're back to our matrix here, that we're a square matrix, a symmetrical square matrix that we have here. And then we have to add in an identity matrix here. Four columns, 4 rows, ones on the diagonal. So what you're going to have in most software packages, you're going to have some case here where you take your whatever matrix you're working with, my A matrix, and then we subtract from it this, and we add in this lambda term here. You can use any term you want, but we just use lambda here for our example, times this identity matrix here, this 4x4 identity matrix. And what you're going to do here, you're going to come up with this new matrix AA here. So you got, let's just look at it. The 103 here, that first squared term, you minus lambda, then 125 minus lambda, 66 minus lambda, and then the last term here, minus 294 minus lambda. So you call out, in this case, a determinant here of a, I could have called that out through this function here, but just the determinant here of your AA matrix here, where you got your lambdas fitted in, you set that equal to 0, and then you're going to come up with a polynomial here. With what it is just got that lambda one term here, so we can solve that pretty easy. We got a lambda squared, and we got a lambda here and a lambda to the fourth here, all set equal to 0 here based on that determinant. So just call out factoring that out here. The polynomial, we got really one unknown here in the squared term, and then just a regular term, just a unit term here, and then to the 4th degree here, powered up to the 4th degree. You factor that out, you come up with your lambdas here, lambda, and then there you go, minus plus 294. This is the factor of this this function here, with just really one term here, the lambda. So that's why we use this lambda here. When you see that lambda in the in your software and different examples here, you use the lambda here. We looked at the rows and columns, x, y, and z, how we came up with it, but we were unable to solve it because of those three unknowns with that polynomial. That's why you're going to use lambda, because then everything comes in terms here with one unknown, and you can factor that out. So factored it out here. That's the factor of that polynomial. You can see they're times each other here, equal to 0. Then you solve it, and you're going to come up with your eigenvalues here. This minus 294. Actually, that really isn't really a vector. It has a position here at 0, but it doesn't have any vector amounts beyond that. So you really don't call that a value here, or eigenvalue here. But the other twos they're all shown here. 147, these are the coordinates, x, y, and z coordinates, minus 0.429. You're going to see everything is in unity here. If it isn't in unity, then you'd have to go back and you'd have to unitize these or normalize these here. But you want to come up with a unit basis, of anything less than 1 here. And that's what it is here. You can see 429 and a minus 8.8 of 0.429 minus 0.857 and then 0.286 here. So that represents that xyz vector from the 0. We're going from the 0 out to this point here for that 147 here eigenvalue here. And that would be, I don't know what it's going to, one of the ideas, one of these vectors here. So eigenvectors here, these are the unit bases. They control the direction that we're looking at in that x, y, z coordinates. And then moving over here, the eigenvalues, they control the magnitude here, x, y, z. The magnitude here is just work. We don't change the direction here. These eigenvectors, these coordinates that are shown here, unless we change it to unity 1, which we're not going to get into right now because that's another subject to talk about here. But all these things is a multiple here of these eigenvectors. This red one here is pointing in the same direction as my green one. It's just going up by what? I don't know. Let's just say it's this 147 here, that one here. It's going 147 and it has these. It's just a multiple of those coordinates here, and I could figure out the coordinates to come up with here. I didn't do that, but they have the same coordinates of these, only multiplied by whatever the eigenvector is here. Okay, so to determine the point here for like this red one, let's just say it's that 147. We just take that times each one of those eigenvector here, 0.429 times 147, and then that would be what? I don't know. It's like 175 or something, and then the other one here, 0.8 minus quantity here, maybe 90, I don't know, and then the 286. That's probably what, 30 or 40 or something like that here. But that gives you the point here for your eigenvalue here, how you trace out your eigenvalues here. Okay, so we just looked through here, we went through it real quick here, and we just wanted to look at how we configure our eigenvectors here, which really, our eigenvalues was based on that lambda, and we had to set that polynomial up here, so we just had one unknown, and we could factor that unknown out here, lambda, based on the different terms we had, powers we had it raised to. We're able to do that, so you can see why that lambda term comes in so important when we set it into that symmetric matrix. And then based on that here, those eigenvalues, the computer gives you the eigenvectors here, the unit amount for those eigenvectors. Okay, so that'll end our discussion here on how we would set up a square matrix here for this quadratic function, and we looked specifically at an ellipsoid here. Okay, so that'll end our discussion.